Breaking the wall of the dark cosmos. How astronomy explores the past, present, and future of the universe. Brian Schmidt, Australian National University, Canberra.
On the 9th of November 1989, I was a PhD student at Harvard. I remember that the news spread throughout the observatory, and I went into a common room and watched it happen on TV.
So today I'm going to tell you about three big questions that astronomers should be able to break down the walls using technology over the coming decades. But let's start with a picture of stars that most of you have seen, the Pleiades, often referred to as the Seven Sisters here in European cultures, but more interestingly to me, also within the Australian Aboriginal culture. It is a story shared from millennia ago. Understanding the stars have been uniting humanity throughout our histories. And even in the oldest pictures that we have, for example, on the cave of Lascaux, 17,300 years, we see the Pleiades up there right next to the bull, which we still today call Taurus. So, our first question that we want to talk about is, what is the life history of the universe? And to help prevent future interactions, I think I'm going to have Klaus come up here and be Atlas. And Klaus, I want you to create the universe, okay? So, good luck. 1929, Edwin Hubble went out and he measured the universe for the first time. He measured how far galaxies were away by how bright their stars were. And he also went through and he measured that they were moving away from us. And he found that the further the object was away, the faster its motion. And just like a balloon expanding, where you see the same thing, he concluded that the universe was expanding. In our balloon, the Big Bang is at the center, where everything was at the beginning. And as the universe expands, it expands into the future. Thank you. I hope not to see you again. So, if the universe is expanding, we can think about what happens when we put it into reverse. Things are closer. Things are closer and on top of each other, and there is a time when everything in the universe is on top of everything else, the time of the Big Bang. So when we look back into the past, we look to a time that is different. A time, for example, when we look back so far that light has taken 12.5 billion years to reach us, we're looking back to a time here where galaxies are closer together, the universe is denser, and it turns out the universe is hotter. If we look back 13.8 billion years into the past, we look back to a time we call the Dark Ages, a time when the universe is empty of stars and galaxies that we see today. We can look back further, not with a telescope like the Hubble that sees optical light, but rather with one that sees radio waves. This is a picture of the universe 380,000 years after the Big Bang, where we see sound waves rippling around the universe. The universe is 1 billion times denser at this time, and it's 1,000 times hotter, 3,000 degrees, and glowing like the sun. We can go back even further still, not by seeing, but by understanding. If we go back to 1 second, the universe is 10 billion degrees in temperature and 10 to the 18 times more dense than it is today. At that time, nuclear reactions, the same that work here in our own sun, occur, and you are able to create from the protons and neutrons the universe was born with, helium. And the nuclear reactions are well understood, and we can predict very precisely that the Big Bang made a universe 75% hydrogen, 25% helium. When we look back with a telescope like Hubble, we see a universe very rich of galaxies. We're looking back to a time here, as I said, 12.5 billion years in the past. But we're not yet able to see the first stars and galaxies. That will be able to happen, we think, in the next few years. The James Webb Space Telescope will give unprecedented ability to look back in time and for us to see the first stars and galaxies as they form. Now, this is a picture which we think James Webb will see, and you will see many, many tiny galaxies that we expect to see. Those are the first stars and galaxies, and will give us an insight to how everything came from nothing. Now, when I showed you this picture 50 million years after the Big Bang, it's empty. But if you can look with radio eyes, you'd see something much more exciting. And that's because hydrogen glows in radio waves, not so much when it's cold in optical. And as hydrogen is able to essentially transition from its electron getting disoriented to its proton, a radio wave is emitted. And so in Western Australia, for example, and also in Holland, there is a new style of radio telescope out away from FM radio radiation that is human-made, and we are building arrays of telescopes to look to this epoch for the first time. This is anticipation of an even larger radio telescope, the Square Kilometre Array, to be built in southern Africa and Australia. I'm impatient, and we have around us a fossil record of 100 billion stars. And so using a telescope in Australia known as SkyMapper, and ESA, for example, is mapping this with a satellite known as Gaia, we can go through and look for the most primitive stars. Last year, we found the first star that had no iron in it. A star we think was born from one of the first stars. Our first fossil record, we expect to find hundreds of similar objects over the coming years. Let's talk about our next question. Are there Earth-like planets that host life? When we go out and look in the past, on the day the wall came down, there were no exoplanets known. 5 years later, 20 years ago, our first. Today, we find there are nearly 2,000 confirmed planets. Most of these have been discovered through something known as a transit. Venus here going in front of our sun caused our sun to dim just a little bit. And with a satellite known as Kepler, many, many hundreds, well, thousands now of these planets have been discovered through this technique. It's very difficult to discover an Earth. You miss most of them. But despite that, we have found Earths, or Earth-like objects out there. And we can estimate that the average star like the sun has a planet not dissimilar to the Earth. And so in the coming decade, NASA first with TESS and ESA later with Plato will be surveying all the bright stars in the sky looking for Earth-like planets. And this is exciting because here is a picture of Venus. And you can see at the rim of Venus light bending through the atmosphere. And that light, as it bends through the atmosphere, will pick up the fingerprint of what is in that atmosphere. We hope to be able to look for example, oxygen, which presence here on Earth is due to life in external planets if they do contain life like here on Earth. The new telescopes, for example, the European ELT, the Giant Magellan Telescope, and the TMT Telescope, plus the James Webb Space Telescope, are the technology that break down the tyranny of distance that keeps us from doing this at present. My final question, and these are by no means all of the questions, are what are dark matter and dark energy? In 1998, I was part of one of two teams that made an unexpected discovery. We went back and we measured how fast the universe was expanding back in time. And here is the data from 1998. We compared nearby objects to distant objects. And you can see that the distant objects apparently showed that the universe was expanding slower in the past and that we had sped up over the last 6 billion years. Speeding up was not expected because gravity should pull. Well, not expected unless perhaps you are Albert Einstein. Albert Einstein in 1917 thought of something he called the cosmological constant, energy that is part of the fabric of space itself. And in his theory, energy that is part of space causes gravity to push rather than pull. Our supernova observations of the distant universe, which I showed you earlier, indicated that the universe must be 70% stuff that pushes, this dark energy, 30% stuff that pulls. Dark matter we have seen since the 1930s. Everywhere we look, there is more gravity than there is atoms, than there are atoms. So here we see two clusters coming together. And when we look at this, we can see the atoms. They emit X-rays, and they are crashed together in the center. The stuff that we call dark matter has seemingly passed through, and we see the dark matter only by gravity. It distorts space just a little bit, and we can pick it up by the distortion of galaxies. And so everywhere we see dark matter, we infer it has gravity, just like atoms, but it does not interact. It can pass right through itself. Now, we suspect it may not always pass through itself. It just does it almost all the time. So there are ways of detecting it in the future. One way to do is just to look at those sound waves. When you drop water in a pond, and that is a picture of the universe, a giant pond, the wave action depends on what the pond is made out of. A pond made of water is different than a pond made of honey, for example. And so the Big Bang, it turns out, was equivalent to throwing gravel into the universe. And those waves reflected about for 380,000 years, and then we get a picture of it in this early time of the universe. And that picture allows us to see the wave action, and it tells us, indeed, 25% of the universe seems to be dark matter. 5% of the universe is atoms. And it also, it turns out, confirms 70% of the universe is this stuff called dark energy. So we see it, but we don't understand it. We see dark matter, we see dark energy, but why are they there? So that is a big question for going forward. For dark matter, we can hope perhaps to create it in the Large Hadron Collider if it is a particle, as we suspect. We might also be able to see it when it very rarely, for example, interacts with xenon in an underground mine that blocks out everything else, because dark matter can travel right through the Earth, and only occasionally would we expect it to run into an atom, very, very rarely. Finally, we can imagine seeing it directly astrophysically, because we suspect that dark matter may occasionally interact with itself and create gamma rays, and new telescopes and existing telescopes are mapping out, for example, in the center of galaxies to see if indeed there are these gamma rays there. Dark energy is much harder. The only way we know how to see if dark energy is there at present is to see if it gets created exactly as space is created, as Albert Einstein said. So we can say, ask the question, does dark energy accelerate the universe like Einstein predicts? We're doing huge surveys with the world's largest digital cameras, literally petabytes of data sifting through these very rare objects. And so these experiments have of yet only seen evidence that dark energy behaves like Einstein has predicted thus far. And we have a lot more data. This is how many supernovae we have. And we have new ideas. For example, looking at the sound waves which give you galaxies and seeing those sound waves imprinted in the galaxies of today. These are our techniques for discovering and understanding dark energy. But time is running out. Well, at least from an astronomer's point of view, because our sun over the next billion years will expand and boil off the oceans of Earth. So within the billion years, we need to get out and make sure that we are able to go and have another place to live. But there seems to be one impenetrable wall of time, which is no matter what we do, the dark energy is going through and being created, making the universe run away. And so the universe, my universe, will carefully and quickly fade away before our eyes. And the galaxies we see today will literally fade away. Thank you very much.